Okay, the subject of phase is one that a lot of people feel a little intimidated by, but that's only because it's perceived as being highly technical and it does hide behind a little bit of specialized vocabulary. But once you're through that vocabulary barrier, this is actually pretty approachable stuff. If we look at any sound source and the waveform that it produces, and we compare it to another identical waveform, you can describe their relationship in terms of phase. And if the peaks of one wave line up with the peaks of another, then these two waves are said to be in phase. And if we assign the peaks an arbitrary value of 1 for demonstration purposes, if you combine a positive 1 with another positive 1, you get 2. So playing back these waveforms together is going to result in a combined waveform that's twice the amplitude of the constituent parts. So in other words, waveforms which are in phase reinforce each other. However, if we change the experiment a little, and in this example, say we shove one of those speaker cabinets a little too far forward of the other, and now produce, again, identical waveforms, we're going to see that the valley of one is lining up with the peak of the other. And that valley has an arbitrary value of -1. If we combine -1 and +1, we get 0. So if you play these two waveforms back, they're going to cancel each other. And this cancellation can be either acoustic or electronic in nature. But don't take my word for it. Let's look at an example. Okay, for this demonstration, we'll get to look at another cool feature that WaveLab offers. Coming over to the File tab and down to the Tools tab, we're going to select the Signal Generator. And this is going to allow us to create raw signal for all sorts of purposes. For this demonstration, we'll stick with a sine wave. We're going to set an arbitrary frequency of 1,000 hertz. And I've got a level here of -3. But set those parameters for whatever you want. And when we hit generate, it's going to create a new tab with this sine wave on it. So there we have our new tab called Untitled 1 in the active tab group. Let's just take a listen to that. You'll hear a mathematically perfect sine wave. Okay, now let's zoom in all the way on the bottom half of the screen. And we get down to almost the sample level, and you can see that both the left and right channel are perfectly in phase with one another. Now, I'm going to use some of the tools that we looked at in the earlier chapters to select all of this and then limit my selection to the right channel only. So if you look in the upper display, you can see that the entire right channel of this audio editor is now highlighted. And with that selection made, come over to the Process tab, and let's see what the Invert Phase option is going to get us. Sure enough, it flipped the right channel upside down. And now to get these two to play back simultaneously, essentially to layer them on top of each other, I'm going to come to the Master section, go to the Audio Channels dialog, and I'm going to tell the system to mix the output to mono. And now, zoom out and move back to the beginning of this, and let's hear what it sounds like out of phase. Canceled to absolute silence. Okay, now I'm going to take this back out of mono so the two channels can play through their default routing. And let's take a look at a more real-world example. If we come back to this first tab, the one I've called Brave Phase, I'm going to play this. I want you to pay close attention to how it sounds from about 6 seconds to about 12 seconds. Okay, you can definitely hear that something changed. It didn't change for the better, but this gets back to what I was saying earlier about the appropriate use of meters versus ears. I'm going to play that section again and look at the spectrometer, the spectroscope, the wave scope. None of these visual tools are going to really show anything wrong at all. Take a look. I'll play this back and we'll take a listen to that, or to look at that. Okay, so we can definitely hear something's wrong, but if you were depending just on any of those meters, you wouldn't see it. Now, that's obviously a phase problem, And what I want to show you now is what a phase problem looks like. So we'll change this to the phase scope in the upper right-hand corner. We'll jump to the end of the song or further back in the song where the phase problem has been fixed. And I want you to take a look at how properly mixed stuff is going to appear. And essentially what you'll see is a distribution basically along the vertical axis. The other thing that you'll notice at the bottom is that the energy distribution is to the positive side, so between the 0 and the +1, and that's, again, that's what we want to see. See, most of that scatter plot is hanging out along the vertical axis. Now let's go back to the top, and we'll play it in again. And again, pay attention to how the phase scope changes from about 6 seconds to 11 seconds. And it'll be obvious because it's going to correlate with that sort of hollow or missing sound that you heard a moment ago. Okay, so the most basic use of a phase scope checking for phase problems in a stereo mix like this is that an out of phase signal is going to give you a lot of activity on the horizontal axis and not the vertical axis. Let me run through that one more time so you can take a listen, take a look. You get a mix, presumably one sent to you from someone else, and it doesn't sound right, or somebody says, hey, can you troubleshoot this? Because it's all there, but it just sounds hollow or it isn't working right. If you don't know anything about this piece of music, you're going to be asking, is this an EQ problem? Is this a normalization problem? Is it a phase problem? And if the whole thing is screwed up, as opposed to going in and out like this demo, it may not be immediately obvious, and that's where the phase scope can rule in or rule out an issue. If it sounds funky and you start playback and all your phase energy is located primarily along that vertical axis, you can say, okay, well, it's in phase or primarily in phase, so that's not it, and you can begin exploring other fixes. Conversely, if you cue it up and you get this on the phase scope, don't even try attacking this with EQ or some other processor, because that's not going to, well, with one exception, that's not going to do it. So it's a diagnostic tool for phase. The scope here is invaluable. But that leaves us at a quandary. Okay, we've identified that there's a phase problem in a piece of material. How do we go about fixing it? Okay, in terms of fixing phase problems, we essentially have 4 avenues of attack. And the first one is to avoid the problem in the first place. And the single biggest thing you can do to avoid phase issues is apply the 3-to-1 rule. Now, if you think about the 2 most difficult things for a new engineer to record, it's typically the acoustic piano and the acoustic guitar. And the reason why, I think, is that everyone seems to know we're going to need more than one microphone, but they're not really sure how to position them. And the 3-to-1 rule states that if you're using 2 microphones to record a common source, those microphones should be 3 times further apart than they are from the sound source. So in other words, if we're going to hang 2 mics over the harp of an acoustic piano, and let's say they're going to be 1 foot off the harp, then those mics need to be at least 3 feet from one another. And if you apply the 3-to-1 rule, it's not an absolute guarantee. This is a rule of thumb, but your odds of incurring phase problems drop precipitously. Okay, our second option is to invert one of the channel's polarity. And this is typically your best mode of attack when you've got multi-channel drum problems. Now we're looking at the channel settings dialog from Cubase here, and you'll notice down by the pre-gain, you have a 0 with a backwards line through it, and that is the icon or the symbol for phase invert. So if you have a situation, again, now we're back, this doesn't help us in WaveLab, this is back at the recording or mixing phase of the process, but so that we understand end to end. If you have a drum mix where it's just sounding washy or unfocused, one of the oldest tricks in the book is just to go through channel by channel and flip the phase of each mic until the mix comes back to life. It's a little bit crude, but it's amazing how often that and that alone will fix it. Our third option, and this is something that's probably more relevant to a WaveLab type environment, and again, especially with drums, is you may have to go in and visually align the transients in order to get those waveforms back in step with one another. And if all else fails, there are phase alignment plugins out there. And one that works particularly well with the Steinberg products is the Vox & Go. Of course, there's a lot of Vox & Go code that's baked into Cubase, that's baked into Wavelab and so forth. And so it's a great place to start. But this certainly isn't the only solution, but there are phase correction plugins available that you can slap across a stereo bus or onto a problem channel. And again, it's not a 100% solution, but it's essentially doing that transient alignment that we just saw, but it's doing it automatically on a sample level, and it's doing it across the entire piece much faster than you or I could ever go in and edit them by hand. Now, before we conclude our discussion of phase, I just want to point out that there are actually some very positive applications for phase shift. What we've really been talking about here all along is known as common mode rejection, and that simply states that if you phase invert one half of a stereo field, whatever's common to both channels will be rejected or canceled. In the case of our sine wave demonstration, since the entire waveform was common to both sides, the entire waveform was rejected, and we ended up with silence. If you've ever seen an advertisement for one of those vocal eraser machines that claims you can play any piece of music through it and it'll remove the vocals so you can sing along, that's all in the world they're doing, is taking one half of the stereo field, phase inverting it, and then recombining the two. And they're banking on the fact that most vocals are panned to the center of the stereo field. But it also tends to reject the kick drum, the bass drum, and they sound horrible. But that's how those things work. Now, on a more salient note, if you look at a balanced audio connection, also known as an XLR connection in most applications, it's using the same phenomena. And in fact, you'll see the acronym XLR stands for the fact that it's crossing the left and right as it travels down the cable. If we take a balanced audio connection and we connect it to a mate, what's going to happen is that the audio traveling down pin 2 is going to be phase flipped coming out of component 1 and then phase flipped going back into component 2. And the same for its companion piece. It's going to be phase flipped at each end. So the audio actually travels down a balanced connector out of phase with itself. And the reason why is if any interference or noise is induced on the way down the cable, that noise will affect both conductors identically, which means when they phase invert at the other end, the noise is out of phase with itself, but the signal is back in phase. And now the out of phase noise cancels, falls off the signal, and you're left with pristine audio at the other end.